right, it looks like everybody's back well enough. We're rearranging the schedule a little bit today, so I will be presenting this morning about standards and calibration curves, and Lindsay's taking the afternoon spot right after lunch to discuss stability, reproducibility, and validation, just so that you know. All right, so here, again, if you haven't downloaded it, it will be helpful because we have some hands-on section coming toward the end. Okay, so let's talk standards. Why use them? We discussed this a little bit yesterday, and Andy went over a lot of details about different kinds of standards and how they impact the quantitative results. Why use them? Because we just want to spend money on stuff, and you know. I find that they're really handy. Even if I haven't developed a method yet, sometimes having standards to practice on is very nice. It gives me a little bit of a sense of comfort to make sure that if I spike them in my sample, they're chromatographically co-eluting, they're fragmenting similarly, and then I can do optimization on standards. So standards don't always need to be isotopically labeled. You can purchase light versions of them, synthetic peptides. But just from a very simple point of view, they're nice to work with. So the types of standards that you can use are internal or external. What kinds of standards? We've gone over this a little bit. There are peptides, either specific to the peptide you're monitoring, or general peptides that are in the chromatographic gradient that you can normalize things to, like labeled reference peptide. Extended peptides, does anyone know what these are? These, I don't know if there's like a proper name for them.
If you want to actually digest rather than just have the peptide.
Right, so it's the tryptic peptide is synthesized with the additional amino acid sequence that's present in the protein, so that you spike the entire thing in, and trypsin can go in and cleave at the tryptic cleavage sites. So these tend to be synthesized longer, and yeah, we'll get into those in a minute. There are protein standards, and then there are also ways that you can isotopically label your sample. So SILAC is an option if you're growing your cells in culture. And there are other things like digesting in O18 water. If you do this, trypsin will replace the oxygen with an O18 version, and so all of your peptides will have an addition of a couple mass units. And this can be expensive and can require a bit of method development, and everything in your sample will be modified, and then you can mix it with the light version. So you can create what's called a global reference standard in that case, if you're working with things that cannot be labeled in culture. Okay, so why use standards? And Andy kept saying something that I liked a lot earlier, which is don't just take the peak area ratio and multiply it by whatever heavy you spiked in, because that's not what we do. And I like to point out as much as I can that quantitation using mass spectrometry is all relative. Even if you have an internal standard, whether you have an external standard, whatever you're calculating is all relative to one of those other things. It isn't like Beer's law. It isn't like absorption, where you can look up in a table extinction coefficient, calculate what that is, where you know the path length, and you can measure the absorbance to calculate a concentration. You can measure intensity, but there's this variability factor that's included with ionization, digestion efficiency, recovery stability, and so on, that we can't really account for, and day to day this may change. So this is why it's important to include a standard to help minimize the variation, and the higher up in the workflow you include these standards, the better off you are able to account for those things. So standards account for some of the variability at sample prep. In the auto sampler, how many times have you ever had your system, your LC-MS, do an injection and the peak area is like half of what you expected, or you didn't get any signal? And a lot of people automatically like, the mass spec is broken. But many times it's just the auto sampler didn't pick up your sample. And if your peak area of what you're monitoring is half and your internal standard peak area is half, then you know it's probably not the sample. It's something along the lines of the LC or the MS. It takes into account any issues with your column. If you didn't equilibrate your column and all of your peptides came off right in the beginning, then both of the internal standard and your sample will act, your peptide will act the same. Electrospray stability, how many people do nanoflow and often see dropouts in their signal? You'll get a nice, not a nice profile peak, but you'll get something with like Bart Simpson hair, or it's just jaggedy. So if your internal standard does that as well, then that helps to account for that variability. And then obviously detection. If there is a problem with the mass spectrometer and it's not giving you the intended abundance or intensity that you would anticipate, both your internal standard and analyte should be consistent. So one of the ways that internal standards help account for variability, this is shown where I was plotting intensity of, or peak area of an analyte versus its concentration on the column. And this is just raw peak area. If I take and I normalize the peak area of the analyte to an internal standard, watch what happens to those points on the line. They kind of go right down to the line, and it helps minimize the variability. The plot here, we can't really get a whole ton of information because we've got peak area ratio versus amount of analyte. If we were to plot ratio of analyte, this is where we would hope to see a y equals x relationship, where the change in the concentration of the analyte is proportional to the change in the intensity of the analyte. Okay, so here, differences between internal and external standards. With mass spectrometry, the best way to have a method that gives you the most useful data is to include it in internal standard as early in the workflow as possible. But many times this isn't possible. So if you are able to include it early on, like, I don't know, if you dream big dreams and think about when you go and have your blood sample, maybe there's something in the vacutainer. Like, how awesome would that be? Like, heavy labeled peptides that are already there, heavy labeled proteins that are already there. Or better yet, before you get your blood sample, the day before, you drink something that like heavy labels all your proteins, right? I mean, who knows? Maybe one day we could get there. They do it in rats, right? So sample prep, that's one of the first things when blood is sampled and it sits for a period of time in a cooler before it can go and get spun down to generate plasma or serum. That's already sample handling. How the blood is drawn from you is sample handling. Let's see. Internal standards can account for variability in all of these things that are related to the LC-MS separation. And they can also aid in interference issues. As we talked about yesterday, the relative intensities of the product ions can give you, they have to match between light and heavy. There's no reason why they should not, except for two reasons. One is interference. Does anyone know what the other reason is? So these patterns that the peptides produce when they're fragmented, they should be identical all the time, except for interferences, which we learned that yesterday. Or if one of those peptides is below the limit of quantitation, then those intensities and that pattern is less predictable. The mass to charge of those ions, those product ions, will be consistent, but we can't guarantee that the tallest ion will be always the tallest product ion and the smallest will be the smallest, because there just aren't enough ions to do it reproducibly below the limit of quantitation. So that's why it's always nice to have more than one product ion when you're monitoring these peptides. I always go for a minimum of 3 if I have an internal standard, and if I don't have an internal standard, I go for more, like at least 5. All right, external standards don't account for all of that sample handling and analysis variability. They allow for comparison of your sample to a standard and maybe across a series of analyses, and they may aid in interference issues, but they may not, because maybe it's not in the exact same sample you're monitoring. And so this again is where I would say more transitions the better if you don't have an internal standard present in the sample. So, and Andy had touched on this too, external standards may not account for the sample matrix differences. The best way to figure out, particularly if you're going to be running a method in a lot of different samples from different sources and you're looking at biological variability, then it's a good idea to test everything. in different plasma samples or different potential cell lines that may be from the same type of cancer, for example. And this way you can see if you're getting a linear response, if you're seeing things tail out on the bottom or saturate at the top. And this is an example using absorbance, again, but a lot of the issues that are observed there are similar with mass spectrometry. We can still see the saturation at the top and hope for as straight a line as possible, but many times it doesn't happen. So for use of internal standards, again, as I mentioned, ideally you want to have everything added in as close to the starting point of you acquiring the sample as possible. And there's been a lot of movement on heavy protein standards. One of the things that is difficult is how are they made? So does anyone know how heavy protein standards are made? What's that?
They're cultured with heavy amino acids.
Right, so they can be grown in culture and expressed by whatever organism with heavy media. So I think the less expensive way is having uniformly incorporated N15, because I think it's like, do you know, Andy, how they do? Is it like glucose, heavy glucose that they put into the media? Okay. Right. So so when they're grown like that, then every nitrogen in your protein has N15 or is supposed to. Well, the incorporation isn't always 100%. Does anyone know why that's not always a great thing? This is very mass spectrometry specific.
Match to match variability or
Potentially. However, for how many people use high-res accurate mass instruments? How many people look at your mass spectra, at the MS1 scans? Right, so normally, if this is mass to charge, when you see a +2 charged peptide, it tends to have a pattern like this, right? This is the M plus H, this is the M plus 1, the M plus 2, and their separation is by 0.5 mass to charge units. And so this is how we know it's a +2 charge state, where the isotopic distribution looks like this. If you, +3 would be something, well, if it's for the same peptide, it'll be down here. And it might look like this, where this is the monoisotopic. And so this is an important thing. This is partly what Skyline does to match precursor isotopic pattern. This can be theoretically calculated. When you have isotopically labeled peptides, but the incorporation is not 100%, then what you have is appearance of the underlabeled forms showing up here. And there's a broader distribution of this because it's not fully and purely isotopically labeled. So when you go to isolate it, you might go to isolate the most intense peak, but that might not be the fully labeled isotopically incorporated precursor. And so that means your heavy protein isn't 100% pure because it doesn't have all N15 at every single atom. And so that just makes it a little challenging because you kind of have to multiply the incorporation by all of the nitrogens in the system and in the protein. And so you don't always get much anywhere near close to 100%. If you use heavy amino acids in culture like C13 and 15, and those go into the peptide backbone, and they're digested with trypsin, those have a higher chance for isotopic purity, and so you don't have this weird distribution issue. I actually have slides that can show you a little bit about that, but I can do that later. So this is, so that's one problem with those, but obviously they're kind of the best things that we can do to get incorporated high up into the workflow. There's also the issue of once they're expressed, how pure are they? What other things are in there? Does anyone know how we quantify pure proteins? how would you quantify a protein that you're going to use as a standard? You want to spike in, a picomole into your sample. How do you know? You just read the concentration on the tube, right? But who told you that concentration?
Could take it all the way to amino acids and do amino acid analysis.
Right, so some people use amino acid analysis. And amino acid analysis, you take your sample with a fixed volume and you hydrolyze it with strong acid like hydrochloric acid, and it breaks up all of the amino acids individually. And then you look at that in comparison to a standard, either using fluorescence, it's always chromatography based, sometimes CE. And then you base the concentration of what you've measured to some external standard. And do you know what the variability of this measurement is? It's like 30%. It's not very precise, so already you've got an internal standard that you haven't digested yet. It may not be pure, and the actual concentration you've been given to write on the tube is plus or minus 30%. So this is not great. This is why it's hard to get an absolute quantitation value in mass spectrometry, which is why I don't like using that word absolute. Okay. So here you can see where you would incorporate all of these things into the workflow. If you use synthetic peptide standards that are already tryptic digested, they can be incorporated during the digestion procedure or after the desalting, and where they're put in will have an impact on what quantitative value you get out. You put them in before desalting, then they will go through the desalting process, account for variability with your analyte. You put them after the desalting process, then they don't. And you don't get this variability addressed. You might have losses here that aren't accounted for. And so again, it's just not an absolute quantitation kind of way to generate values. Okay. So I touched on this briefly yesterday. Labeled reference peptides are a nice way to inexpensively sort of help to minimize variability in the LC and MS portions of your workflow. You can buy heavy peptide labeled kits from Biognosis or Pierce, and these are multiple peptides that you can spike into a sample, and then you normalize all of your analytes to like either the nearest one or an average of the heavy labeled peptides present in the sample. This helps minimize the variability. Depending on where you add them in, it could be variability due to desal, autosampler, MS, and so on. It's a lesser expensive alternative, but still, it's not perfect. And I showed these yesterday where if you have an internal standard for a particular peptide, the coefficient of variation is very low. If you use a labeled reference peptide, it gets a little bit higher. And then if you do label free and just look at absolute peak area, the variability is not accounted for. And so this is as raw as you can get from the data that's generated. Who here uses synthetic peptides? I've got some people, okay. They're pretty easily synthesized within a certain size. They can incorporate heavy amino acids. They're getting less expensive, but they still can be an initial investment where it's about $500 to generate a significant amount. It'll last you a very long time, unless you're like me and you spill stuff, or you lose it in the freezer, or you kick it under the -80 and didn't know. So you have to be very careful about that. However, at least the ones that we've worked with, if they contain a cysteine residue, we ask that they're synthesized with the alkylation intact. And so they wouldn't account for reduction alkylation, obviously not digestion, and so on. So this is an example of the first CPTAC study that was published in 2009, where it's looking at a peptide from CRP, and there are 3, so this is one site that analyzed this peptide, and this is another site that analyzed the peptide, and then each of these horizontal boxes is a different study. So in the first study, these labs were given digested plasma with the light and heavy peptides spiked into a response curve where the heavy was spiked in a fixed amount and the light concentration varied. And this is plotting the peak area ratio of those transitions. And you can see the difference between these two labs. The slope is not the same. It's hard to explain that. They're using the same type of mass spectrometer too, so not entirely sure what was going on there. Here, in this study, each lab was given samples where the light protein was digested and the plasma background was digested separately. And then they were mixed together, and heavy peptides spiked in to generate the same response curve. And so this deviation from this slope of 1 is most likely caused by digestion of the light protein. It wasn't 100%. Or it could be that we didn't know the concentration of the protein when we started, right? Because amino acid analysis isn't very accurate or precise. And then again, the slope is different between the two sites. And then the last example is the light protein was spiked into plasma before digestion. And so now we're looking at the effect, the loss and recovery of that peptide from that protein that was spiked into plasma and then had to be digested with all the other plasma proteins. And so this is a little scary. If you look at which internal standard are you going to use? Are you going to use a peptide standard? Are you going to use a protein standard that's digested and then spiked into your sample after your sample's digested? Because now those are two different parallel digestions. Or if you spike it into your sample, are you going to detect it, right? So these are all things that you kind of have to take into account when you're doing this. This paper came out a couple of years ago, a few years ago, I guess, where it was looking at, and Andy touched on this too, how do you know when your digestion is complete? And at this point, at least I always go for, is it reproducible? If we can get it to a point where you have a stop time for your digestion and you give it wiggle room of plus or minus an hour or two, something where if someone didn't get back and quench the digest, it still give you the same kind of result. That would be great, but this is the kind of response we would want to see, where you have release of a peptide and it's stabilized. And if you spike in your internal standards and they go through the digestion process, if they're not stable and they begin to decay, you want to make sure that they decay at the same kind of rate as your analyte and not at a different rate, because then the quantitative value will differ at different time points. So several years ago, I worked on this project that we called the winged peptide standards at Broad, and this thing was a nightmare. We wanted to see if using winged peptides, so including this native amino acid sequence on either end of the N and C terminal tryptic cleavage sites, if this would have an effect, if it would improve calculated recovery, if it would lead to more precise and accurate measurements for quantitation. So the problem is the tryptic peptides that we use are of a certain size, and now you add amino acids onto either end and they quickly become bigger because you're always adding one to each side, so that's 2, 4, 6, 8 amino acids. This makes them harder to synthesize, and then their solubility can get in the way. So and you can't take what the synthesis company has given you and analyze and get precursor and product ions of what you want until you digest it. So that makes it extra tricky. However, if it works, the benefits are that the digestion variability is minimized, so it's not as bad as spiking in a tryptic peptide standard, so it may improve the accuracy. But how do you know their exact concentration? And again, this goes back to how do you calibrate your calibrant? How do you know what the concentration is? Do you use amino acid analysis? Do you use LCUV? If we use absorbance, we can calculate what the absorbance should be at certain concentrations, particularly if there are chromophores, which some peptides have. Fluorescence is more sensitive, so maybe we could use that aspect, but these are not commonly used techniques. Most mass spec labs don't have a spectrophlorimeter or one that they can use online.
When you purchase some heavy peptide from, say, New England Peptide, isn't in it the vial says 1 milligram? Isn't that about a milligram?
It's a milligram if they've weighed it, but how do you know that 100% of that milligram is your peptide? There could be incomplete synthesis products that, or degradation products or other things that are accounting for that mass.
Yeah, so like if they say 95% purity or 98% purity, a company like that, for example, do you think they do enough QC for you to be relatively confident that you're looking at 980 micrograms of your peptide?
When you start, that's when I would have the highest confidence, but then as that thing sits in my freezer and I pull it out, thaw it, aliquot it, put those in the freezer, do any kind of dilutions, like the clock starts ticking. So that's kind of the issue is if you purchase a peptide for $500 and it's enough to do thousands of experiments, then how do you make sure that on day 1 you get the same response as on day 30, as on year 1, right? So there are a lot of assumptions that people make where like, oh, it says it on the label, it's totally good. And I've seen experience-wise that peptides have issues, some even at minus 80. And so you can start with a number, but that's probably always going to be the highest concentration of that stock you will ever work with, right? Okay. So we had a bunch of light proteins and their tryptic synthetic peptides that were C13 and 15 labeled at lysine and arginine. Here are these proteins that we were working with. Some of these we even had, I think N50 incorporated proteins too. So this is the tryptic peptide. This was synthesized this way with the heavy amino acids shown in red. And then we had winged peptides where we had 5 amino acids on each side. The idea here is we know trypsin comes in and cleaves after arginine and lysine. But we don't know if there is a local effect based on the amino acid sequence. We know if there are additional lysines or arginines near the N terminus or the C terminus that we can see something like ragged ends where it might cleave at this lysine, and if it does that first, it might not cleave at this one. Or if there's a KK or an RR two in a row, we don't always see 100% of the peptide present in one form. It's often split. So this can cause issues. And we had the company that made these include additional isotopic labels so we could differentiate the tryptic form of this peptide from the tryptic form of this peptide. However, there are other things that we had to consider for peptide stability. What was it? I think this originally in the native sequence is supposed to be a Q, which can cyclize on the N terminus. So this is not the native amino acid sequence as close as it can be, with the N-terminal amino acid not doing something weird in storage. So there are a lot of things to consider. And then if you look at the wing peptide length, everything is like 20 amino acids and greater. So these are pretty big peptides. We also wanted to look at a subset of these peptides and see how long do these wings have to be? Do you have to add 5 or 6 amino acids, or can you get away with just 2? So we had, this is amino acid in each wing, 2 through 6 for all of these peptides. And this is another one where we had it synthesized with asparagine instead of glutamine, I guess, or maybe it was the other way around. But these were all different standards that were synthesized. So we had a ton of different things to look at. And we had the concentration that came with on the little tube sides. So the way we did this experiment is we had these exogenous proteins that were light, that we spiked into plasma. We had the 15 wing peptides that we spiked in at the same time. They went through the same reduction and alkylation process. And then over here, we added in our fully tryptic synthetic C13 and 15 labeled peptides. And then we did characterization and looked at the fragment ions from each of the 3 forms, and they're color-coded just for convenience. And then it started getting weird. So first we did data-dependent runs to see when we do these digestions, what are we actually detecting? So these are showing the forms that we detected from the protein. So this is an undercleaved because this is the full tryptic, but we saw a form that had an N-terminal lysine. So that complicates things. In the wing forms, we saw miscleavage. This is a common miscleavage that we see for CRP in normal biological samples. The hope was that whatever forms, if we saw more than one from the protein, we would see those exact same forms for the wing peptide, and we didn't. So that tells us something right away that, all right, maybe the wing peptides don't work exactly the same way as proteins, but are they close? All right, so this is in a poster from 2011. I can get the PDF if people are interested. But what we tried to do was look at these 3 proteins, troponin T, gamma-synuclein, and annexin A7, and look at the 2 peptides and their recovery when we normalize to the tryptic synthetic peptide and when we normalize to the winged peptide. So it's the protein divided by tryptic synthetic or winged peptide. If we do it based on the winged peptide, assuming the concentration of that winged peptide is accurate, and we matched it to the concentration of the protein we spiked in, we would expect to see a ratio of 1 for every single peptide. Annexin A7, something was up here, so either the winged peptide didn't behave like the protein, or the concentration was off. And that was for this protein, so there's no way really for us to check which effect it was. Over troponin and gamma-synuclein had reasonably good results, and that 20 to 40% difference might be due to us not having matched those concentrations exactly. And then this is what you would normally see, taking that same light peak area from the protein and dividing it by the tryptic synthetic peptide. So this isn't accurate by any stretch of the imagination. And we normalize the responses to the 1 protein from each set so that we could just get a better apples-to-apples comparison. Again, if everything was digested properly and thoroughly and completely, we would expect a 1-to-1 ratio of each of these peptides from the protein, because 1 mole of protein will result in 1 mole of this peptide and 1 mole of this peptide, assuming digestion is complete. But it didn't. So we're seeing less of these other peptides, which again, doesn't point to likely here digestion inefficiency, but when we normalize everything to the winged peptides, we're not really accounting for that in every single case. So then we looked at the effect of the wing length on peptide recovery. So here we're showing the blue bars are the peak areas from the tryptic peptide coming from the protein, and we had a series of different samples, and each sample had the winged peptide with 2 amino acid rings, 3, 4, 5, and 6. So the protein is spiked in the same amount in all samples, and we tried to match the winged peptide concentration with a protein concentration in a mole-mole 1-to-1 ratio. So when there are 2 amino acid wings, we didn't see the winged peptide recovered as well as the protein. And as we increased the wing length, we saw a 1-to-1 when there were 3 amino acids. So we're thinking here maybe trypsin didn't have enough wings around those tryptic cleavage sites to actually go in and cleave. Or could it be that the stock of my wing peptide with the 2 amino acids wasn't accurate? So like, this is the conundrum of like, well, how do we interpret the results if there's no way to know what our starting concentration was precisely? And then we see a similar effect with this peptide, where this is the full length with the 6 amino acids on each side. Here the protein is reproducibly recovered in every single sample, and these are all over-recovered. So if I meant to spike them in a 1-to-1, is it because the protein's not fully digesting, or do I have the concentrations here wrong, or is there some kind of effect going on? So then we had 2 different people repeat it, and they got all different results. So the point of this story is just be careful with what you're calling your standard. And whatever it is, you need to make sure it's reproducible in how you use it, but coming out with a quantitative answer at the end of what you're doing, I would just be very careful. All right, heavy protein standards. Again, we've discussed this a little bit, but these are a lot of the drawbacks that it's hard to account for when you're generating an intact protein standard. However, they are better suited for amino acid analysis than peptides because they have a larger number of amino acids to get broken down, and so you're getting more measurements for protein concentration because you have so many more amino acids to count for when you do amino acid analysis. Okay, so this was a study we did in, it was published in 2015, but I think it started in like 2009, 2010. And here, this was the first time that we had fully N15 incorporated protein standards for, I think it was 25 different proteins. And so when those proteins were digested into peptides, we would monitor their signal. Most of them had different product ion master charge values than the heavy N13 and C15 peptide, or C13 and 15 peptide, and then the red is from the light. So this was awesome because Skyline was able to handle this data. This was probably one of the first times we were able to do this. So what we did is we plotted the light peak area, which was the same exact information in a single raw file. And then on one hand, we would normalize it to the fully tryptic synthetic peptide, the blue signal, the C13 and 15, and plot that in a response curve. And this line here is the x equals y, y equals x value. And so we see that everything, and this is plotted in a log scale visually, if it's offset below the line, we know that means the slope is less than 1. And if we take, for example, one concentration point where we know what we wanted the concentration to be, what we spiked in, the actual recovery value were at about 50%. Is it because the protein wasn't digesting? Is it because the synthetic peptide wasn't spiked in at the right concentration? It's really kind of hard to say. Over here, we use that same light peak area as on the left, but we normalize now to the N15 peak area arising from the protein spike. And when we normalize to that value, everything kind of just jumps up to the line. So here, this indicates to some extent, though the recovery is all around 100%, this indicates to some extent that perhaps some of this loss of recovery is due to protein digestion. So if the light and heavy protein digest to the same extent and it's not complete, as long as they're very similar, then all those data points hop right back up to the line. Again, one step closer to quantitative accuracy, but still not there yet. How many people do SILAC labeling? A couple, all right. So SILAC or a global heavy standard is something you can work with. This provides you heavy signal for all of the stuff in your sample. This can be beneficial if you're not really doing particular targets, but you're doing, global screening to see what changes are occurring. And then, as I mentioned before, there's this O18 labeling during digestion is another option for if you cannot grow your cells in culture and do SILAC labeling. Okay, so you've chosen your standards. How many people will use standards? How many people don't use them now? How many people don't use them now? Okay. How many people plan on using standards or do? Okay, good. That's good. I'm writing your names down. So what I normally do is I'll construct a response curve. I'll take my standards and I'll take my sample matrix and I will see what the response is over a range of concentrations. Here I can use that information to determine what spike level of that internal standard I will use for my samples because it's something I want to see consistently every time. And then this will also help me determine the concentration range and number of points for generating my figures of merit, like linear range, limits of detection, limits of quantitation. I acquire that data, process the data, and then usually have to repeat it. So, as with many terms, calibration curve and response curve are things that some people use interchangeably. I'm guilty of it too. A calibration curve is different than a response curve. A response curve is showing the change in response of something over a range of concentrations, but it's not calibrating anything. A calibration curve is when you do pretty much the same thing, but you're using it as a calibrant to gauge a concentration or something, whether it's in the same sample or another sample. So what I really mean is response curves, because I don't know what I mean, so we'll get back to that. But the point is you generate something with a range of concentrations and see what the response changes over that concentration range. So what's important to note is how low can you get? Can you get to a zero spike level and see zero peak areas? I don't. I never see zero peak areas. It's very, very rare. The only time I do is when I'm spiking my standards into solvent, right? If you have a chemical matrix like plasma or cell lysate or BSA even, there's usually some non-zero signal here, and so what will happen is this will bottom out, and it's now not linear. So defining the linear range, the point at which it really does have a straight line response, is important because that's when you know that a change in your response is correlated with a change in concentration. Okay, Lindsay will be getting into method validation later, so I'm going to skip this right now. This is a case study where I had touched on a couple of these points earlier, but this is in general how I approach method development and making sure everything's working the way it should. So first, method development, I look at gradient optimization. If I have standards, I will use the standards. If I don't, I will use a representative sample matrix to see how well I can separate everything to give it the best chance for detection and getting enough points across the peak. Transition selection is another important thing. If you only have a triple quad, you kind of have to do these things first before you go on to digestion optimization, because you need to have a method to detect your things before you can digest and detect your things. If you have a high-res accurate master, you could do MS1 detection. That makes it easier to do, and you can skip some of the steps or reorder them. Then I like to look at how much of my heavy isotopically labeled peptide should I spike into my samples. There's no sense in spiking it in a concentration so high when most of the time the analyte you're going to be detecting is 100-fold less concentrated. The ideal way to spike in your heavy is to spike it in just high enough that you can detect it, and also try to match it to the endogenous concentration of your analyte, if that's possible, or at least within a 10-fold swing. And then how do you design your response curve? You want to make sure that you're covering all the points so that you can calculate the limit of detection. And so you're confident that below that point you're not detecting it, and above that point you are. And then you can also determine your limit of quantitation, where below that point you're detecting it, but above that point you can actually quantify small changes. So in this study, we did a lot of this method development at just a few sites and then rolled out phase 2 and phase 3 to a larger number of sites with a lot of different instruments to see how reproducible everything was. So we had 125 peptides that were being monitored that ranged the concentration from 1 attomole per microliter of sample to 100 femtomoles. These were spiked in along with the C13N15 triptych version at 10 femtomole per microliter. So this was a fixed concentration. In phase 2, this was plasma that was already depleted and digested. Everything was spiked in post-digestion. In phase 3, we had these light proteins that are the same sequence as the peptides, the light peptides there, and we had heavy proteins. And those were spiked into plasma that was then digested. And then we also added in the C13 and 15 labeled peptides as a secondary internal standard. And then the third phase was the samples were prepared to generate response curves with the light and the heavy peptides, but they were sent to the sites, and each site did their own digestion and desolved and then spiked the heavy peptides in at the end. And so some of it accounts for digestion variability, some of it accounts for sample handling and digestion variability. This was a big study. This is looking at how much heavy peptide should we spike into a plasma sample so that we can see it every time. So this is 10 femtomole, 5 femtomole, 1 femtomole, and 500 attomole. So here we chose the one that was the most intense. It's not a huge signal, but we wanted to make sure that across the different vendor instruments there were also a series of generations of different instruments. So we had a SciEx 4000 Q-trap and a 5500, and I believe a 6500. So a 6500 would have no problem with that, but the 4000 we would want to make sure that we weren't cutting it off at its knees on not being able to detect reproducibly enough. The other thing you can do with this data is if you don't have any light spiked in, you can monitor for the light and see if there's any unlabeled version of the heavy that's giving signal in the light peptide SRMs or MRMs. And this is important because that will always be a factor related to how much of the heavy you spike in. You don't want to artificially inflate what your perceived endogenous signal is if it's actually coming from your internal standard. So this just goes over recommended concentration range for a curve. I mean, if you have an idea of what a biological concentration range will be for your analyte, then start there. If you have no idea, or if you know it is very, very low, then what I normally do is most of these things that I have to look for are not superly concentrated. So I don't have to worry about saturation up at this high end, and I often don't go up that high because it's not necessary for what I need to do. So my upper range, my upper limit of quantitation is defined by my highest point. If we ever get something that reads back higher than that, we call it above the upper limit of quantitation, and we don't quantify it. We just say it's out of the range, right? And then you want to have something that will define the linear range and then define your limit of quantitation and limit of detection. There are dozens of ways to calculate limit of detection and limit of quantitation. The quickest and easiest way is if you run these response curves and you calculate your coefficient of variation at each point, then the point that is like 15 or 20%, and below which you have higher variability than that point at that percent CV or percent RSD, that would be your LOD. And that's a very quick and dirty way of doing it. It tends to be around what you can do with more involved calculations, but it's not personally what I would recommend. I would try to evaluate it more statistically. Okay. Keeping in mind, a lot of people that would like biological content, being able to understand what the moles that we're detecting on the mass spectrometer translates to into mass of protein and plasma. This just gives you an idea where if we detect one atom, mass spectrometers detect moles, right, particularly peptides. And so if we detect one atomole in 1 microgram of plasma matrix, this translates to, with a protein, assuming a molecular weight average of 50 kilodaltons, about 3.5 nanograms per mil. And that's not incredibly impressive, I think, from a clinical standpoint, nanograms per mil. Nothing really exciting is at that concentration, right? Some proteins, yes. Right, but see, that's even like, this is at the very hairy low end of what we can detect, and that's 3 times lower. So this is why we have to do a lot of sample enrichment and other things in order to detect things that are interesting. So here we've got from this phase 2, so this is when the light and the heavy the light proteins were spiked into plasma and then digested, and the heavy synthetic peptides were spiked in. We ran a response curve. This is the linear scale, the same data on the log scale. So you can see, even though this looks straight, right, it's totally not. You get down to this point, and then there's some non-zero peak area that we're picking up. So when we look at the concentrations, this B, C, D, and E range, this is where it's beginning to plateau. And I would like to precisely know what my limit of detection and quantitation is. I could look at it and say like, oh, that one's on the line, but maybe that one's not, so somewhere in there. But I kind of want to know what it is reproducibly so I can calculate it every single time I run this method. So there is a method of determining limit of detection in the external tool in Skyline called Quasar. So it will use one method of LOD calculation to determine that for you for all of your analytes. But here, what was interesting is if we look at this distribution of LODs, so this bar represents every site had 125 peptides that had LODs calculated for them. So the interquartile range is represented in the median LOD across all those peptides is shown. The idea here was we just wanted to get a sense of how reproducible the limit of detection was determined at all these sites. And we had some sites that had lower ones and did better, and some sites that had a very narrow distribution of limit of detection, while others were higher and broader. And this is just what you see when people are doing science, unfortunately. And if we look over here, and these points are outliers. If we look over here, this is when the data were normalized in order to calculate limit of detection. We still use peak area ratio. And here the peak area ratio was determined by normalizing to the N15 heavy labeled protein. And so what you can see is these axes are not on the same scale. So these guys are all the limits of detection are higher, even though we're detecting the same exact light thing. They're all higher because when we put the heavy proteins in, they're not recovered at 100%. And so it accounts for variability, but unfortunately, it doesn't improve our limit of detection. So the quality of the data may be better, but we can't claim that it's as sensitive or more sensitive than using the N15, C13 labeled peptides. So this is something that could easily be misinterpreted. People could say, oh, I'll just use peptides as my internal standard and I'll have a more sensitive assay. You may, it just won't be accurate, right? Because over here we have improved accuracy by using protein internal standards. Okay, and that point is shown here. So in this study, we also had each of the labs run what we called blinded samples, where they didn't know what the concentration was. We just had them run in a certain order, so everybody did it the same way with blanks and all these other things in between. Here is what these, so there were 1, 2, 3 different concentrations. So the theoretical calculated line of what we meant for the concentrations to come back at are shown in these 3 horizontal lines. And then for each site, what was calculated, what was recovered at the end is shown. So everything, all these light blue are way below this line, the medium blue are below the line, and then the dark blue are below that line. So that means it's not accurately quantitating what is present in the sample when we normalize the C13 and 15 standards. However, when we normalize with the proteins, everything pops closer up to the line, and the variability in the peptides that are detected at each site decreases, and so there's much less of a range. And again, this just proves the point that using protein as internal standards, while it may come across as a less sensitive assay, the accuracy is greatly improved. Okay. How do you qualify your standard? Right, so we went over this. Amino acid analysis is no good. Like, how if you start and spike in something and you think it's 10 femtomole, but really it's 0.1 or it's 23, then how do you know you're calculating things accurately at the end? And this is the hard part, is you really don't. How do you know if it's stable in storage? These are things you can test for. So you can look at changes over time, which is a lot of what reproducibility and repeatability address. So the point is test, test, and test again, and then refer to validation. Okay. So we've got 40 minutes to do some hands-on work, and we'll be building calibration curves and reviewing data from one of the CPTAC studies. Are there any questions so far about all that? I think somebody from here should start up their own heavy protein company and just start cranking those babies out. Because at least, I mean, it's not perfect, but somebody has to do it. All right, so if you could open the Skyline file, study 9.2, site 56B, post DS. It may not lay out exactly this way, but let me know if anyone's having trouble. Would be why. Thank you for pointing that out. All right, is everyone here? Great. So I would like to have you click on that first peptide, the ALQA, and then you should see a really similar peak profile as this, where the red is the light signal, the blue is the heavy peptide internal standard, and then the brown is the peptide coming from the N15 protein that was spiked in. And so that you have an idea, going through this study, the blue and the brown should have constant signal throughout because those are our internal standards and those concentrations are fixed. The only peak areas that really should be changing are the red as we go through the different concentration points. All right, does everyone have something that looks like this? This was what you should have downloaded from the website on that early. Did you download it?
Yeah. Well, so it's not from the state.
No, it's not from the thing. This is from the Panorama website. If you have a video presentation of this talk, there's a link on it. Okay. So we're gonna build. Oh yeah. You're getting that because you're click on the proteins, which you will find peptides, and go to the peptides, and you'll see what it is. There you go. And then, for this one, this is peptide, so right click in there and show you that. If you go to view, and then arrange graphs. Oh, God, you got to click right there. Yep, right click in there, and then circle graph. Hey, Brendan, how do you unsplit your view? I don't normally use split view, so how do you
Transitions.
transition? And that's like, okay. Great. Okay. So what I'm going to show you, which I didn't realize Brendan might have done this morning, but setting up a calibration curve or response curve in Skyline. So for these data, I can show you how to do it. Go to peptide settings, quantification, and then set the parameters to those shown. And these are things that you can play around with, particularly regression weighting. The drop downs, your options might be ratio to heavy and ratio to N15. For now, choose the ratio to heavy so you can follow along. All right, okay, good, bless you. Then, if you've not used Skyline before, or even if you have, go into settings, document settings, annotations, and click sample group and internal standard spike. These are things that need to be checked in order to specify what concentrations you used and then replicates of the same sample. And once you do that, you can hit OK. Just also for people who are curious, you can, like this general remarks one it's one that you can add a note particular to a data file. So for example, if you're running a series of samples and there was a little bit of air in the bottom of your autosampler vial for one of your vials and you got no data, but you brought the data in and in Skyline you're like, oh, that looks like crap. Then you can go into general remarks and say, you know, air injected, or you can explain why it's not behaving the way you would expect, which is really handy for record keeping or for sanity checks. Okay, everyone with me? Good.
My annotation is blank. There's nothing in
You have to set up your annotations.
If you have the quasar tool set up, you should have
disclosure, I wasn't here yesterday, so if I missed something.
But I mean, if you open that, if you have the CTAC file open, you should have that too.
Isn't that weird?
But I think I'll just follow along.
Well, I'm confused. Yeah.
If when you get a version, these slides will help you go through it. Okay. All right, so make sure those are checked and then hit OK. And then if you don't already have the document grid view open, you go to view and document grid. And what I do is I will click and drag this below my chromatograms and I make it the full width of Skyline except for the peptide tree so that I can see things like the file name and all those details. And what you should see is these headers, sample type, analyte concentration, sample group, and internal standard spike. So those are the things that we will go in and modify. All right. Everybody find that?
You're missing some columns.
Which are you missing? Okay. If you go to settings and document settings, then analyte concentration. Yeah. Oh no, that's a different ad type. Hit OK. And then go to views. What view am I in?
Should help.
You right click on one of the headers and see what you can add. Just columns. Yep, all right. If you don't see, particularly the ones you need to see are analyte concentration, sample group, and internal standard spike. If you don't see those, right click in these header areas and choose columns and then check them. I'll just quickly introduce you to my naming scheme for these. So the first set is date acquired, what study we were doing, the site, which has been anonymized, and then the ABC is the concentration key, and then the number after it is the replicate of that concentration, and then CalCurve just means at this point we're running a CalCurve. And what I always do, like ever since I started doing mass spectrometry, is I'll put the run order, like the order the samples ran in, as the last 3 digits so that I can kind of keep track if there are any problems with my data. Okay, so now these are writable, and we're going to fill these up to show Skyline what things are and how to plot them. So the first thing to do is to populate sample group. What this does is it assigns a text or a number to replicates of the same sample so that Skyline knows to group those together. So I just use the key that's in my file name. So A, all of my A's have A, and B's and so on. The sample that has QC in it is our quality control sample. I'm sorry? You can type it in, so I don't know if this Excel file is on the USB drive. It would be an Excel file, and you could copy and paste these into that table. Or if you put the first series, like that A through J, then you can copy this and paste it below too. So there's some little shortcuts like that. Just be aware that down near the bottom, there's a run with an SSS, system suitability sample in it, and that'll kind of throw things off at the bottom if you're copying and pasting. All right. The internal standard spike is super easy. Put 10 in the top cell, and then select the entire column and copy down or fill down. All right, there might not be one. If it's not, I don't have the key. It's not so bad if you can just type it. I'm sorry?
How do you calculate?
Just type in.
Just add a, like for sample group, the first one, okay. Yep.
How's everyone doing? Oh, yep. Click on this views and go to replicates. Okay. So the only thing I did here is I just put 10 in the internal standard spike and I paste it down or fill down. That one's the easiest thing to do. For those of you that are worried that you don't see the retention, it's a different label. So you can, so this, I apologize, this is the results grid. What you see from here on over is what I want you to see in your documents grid. For those of you that want to see the peptide retention time of the ratio to standard, you have to open up the results grid. Right now, keep it in documents grid and just make sure you've got sample type, sample group, internal standard, spike, and analyte concentration.
For the sample groups, does the order just repeat after the first one?
It does, except for down at the bottom, there's that one sample that has SSS in it, and it throws it off. It's in the last set.
At the very, very end?
Yep, very, very end. Don't worry, it'll show up in your plots if you miss it. Okay, so here again, you can type this manually in. If these are your sample IDs that you just entered into that table, these are the actual concentrations in femtomole per microliter. And so if you type it in the first time and leave the QC blank, then you can copy this and paste it in the 3 lower replicate sections. This is something that you have to do in order for Skyline to know where to plot it on the x-axis. They're kind of weird numbers. Sorry. You look confused. Are you okay? I don't think it's in so just if you type it in the first time, so that one column and copy paste that button. It's okay if you don't have it populated in all of the replicates. We'll just get you started. Let me just see. So this is what it should look like. Analyte concentration. Again, leaving that QC blank. And then the last thing, for those of you who are ready, the last thing you need to do is assign the sample type. So these are all drop downs. And for the A, that should be blank, because that's a matrix blank. No light peptide was spiked in. And then for every other one, you would select standard, except for the QC, which would be QC or quality control. You don't have to click drop down, select for every single one. Once you hit the one that's standard, you can click and select all the way down to H and then fill down. It's one of the handy little things. Please ask that. So select that down to just leave it blank, yeah, or unknown. Because it's a complete different set of peptides. It was in there by mistake.
So there's 4-5S.
The SSS sample, leave it as unknown. Don't just ignore it for now. It's down near the bottom. So now, if you'd like to see what a calibration curve looked like, go to View, Calibration Curve, and you should see something that looks like this. If you're on that first peptide, right below the first protein name, it should look like this, if the numbers are all entered correctly. I hope. And you can click through each of the peptides, and it'll show you their response curve for each of those. And so it's just outlining the slope, the y-intercept, the r-squared value, and then the calculated concentration is something it's providing for a particular sample that you might have highlighted. So one thing I like to do, again, is just to view it on the log scale. And the reason there is to see, like, visually, I like to just look and see where my linearity is plateauing at the bottom. I don't do any calculations in this space. If you right-click in this plot, you will have options to show different things. If you include the QC, I think that's what these little green guys are. If you have unknown samples, where you have an internal standard amount in that documents grid, then those would also be plotted on here, whether or not they adhere to the line. I don't know what's going on with my mouse, I'm sorry. And then if you click on a particular sample, it's showing you that sample with a red caret.
Can I just say that after installing the Quasar, I can have those annotations?
They're there, okay, great. Great.
changed that before. I had an error earlier.
Values all tab?
What? You have it, what?
The values all?
Yeah,
Versus
right.
the same value?
If you click on the replicate comparison for retention times. Right click on it.
Right here on the peptide list.
Where it's your retention times, your replicate retention times.
So, to review, it's maybe like the research of
Yeah, probably. I mean, there's two.
Okay, and then, so then,
You can look at performance across all the peptides.
You have all.
So looking at all the peptides, how it is So if you click through the different peptides, you'll be able to see that the curve changes a little bit, whether it's the slope of the curve or the something's happening. Or if it's where that plateau baseline's down at the bottom. And you can also take your curve and you can anchor it. The mouse keeps I know it keeps doing that.
let's just kill it. Let's just kill a mouse.
Oh, it's already.
Excellent.
Okay, thank you.
Dead.
Ah,
Sorry about that.
that's okay. Okay. All right. So then the next thing we want to look at is grouping. We've kind of already done this by defining each sample by a group name. So the A's are all together, the B's are all together, and so on. If you, oh my gosh, if you go in here and you right click, so this is for real, this show. Yeah. You want to go in and right click and select sample group. Group by sample group. So you see where the group by is? Right here. And then move it over to that little caret, and then you've got sample group. So now what you should see is all of your replicates, after you do that, are kind of minimized down into the A through J QC. Everybody be able to see that? Okay.
Can I just quickly share? So a number of people, you don't actually have Skyline running on here. Never mind. Okay. Never mind.
Not a live demo.
Okay.
All right, so when you group by the sample, Skyline does a lot of neat things for you. So it'll plot the average peak area for your peaks, and then the error bar is one standard deviation. So visually you can see how bad your data are if you're averaging this way. And then the lights you should be able to see increasing like that. The retention time, you can see if there are any issues. However, these are based on grouping of replicates, so it may be collapsing things in time or like wrinkling chronological time, so you may not get as much information from the retention time here. But if you click through, again, just click on each peptide and you'll be able to see different things. You might be able to see that some have very good reproducibility, some have very poor, some the peak area for the brown, which is the protein, the heavy protein spike, it may not be consistent. And so you can sort of quickly go through a large volume of data by having a view like this open without actually looking at chromatograms. If you right-click over either in the retention time or the peak area plot, and you click on CV values, it'll convert peak area ratio to heavy to coefficient of variation. And so here now the y-axis is percent CV. And so, you know, low numbers are good, right? Then what's the nice thing about Skyline, I don't know if anyone was aware of this yet. If you right click in here, you can copy this figure into PowerPoint or Excel or Word. Or if you right click and copy data, let's just say for some weird reason you don't like these colors, or you want these numbers, these samples sorted in a different order, it does this alphanumerically. So if we put the concentrations in here, they wouldn't be low to high. They would be like all the ones beginning with 1 and 0.01 and 0.001 would be first. So if you don't like how it's sorted, click copy data, right click, and then you can paste the data into Excel, and then you can plot it yourself. Pick your colors or orders.
Great, so you're saying that the order here can be anything you want it to be. When you import a bunch of data, it will be, you know, alphabetic, but you know, it will be however you imported it. But when you can go into that edit manage results, you can change the order to whatever you want it.
Yeah, but not, this is grouped. So grouping goes alphabetical, and then number-wise, if you have 0.1, 0.001, and 0.001, those will go first, and then anything that's 0.02, 0.2. That's because normally I would group by concentration, so I don't have to have a key to remember what B and C and those numbers are. All right, so you have to tell Russ Grant, because I just searched for this last night, like, oh, let's look up a cartoon about calibrating, and who is this guy? His name is Russ. I didn't edit this, and he's talking about calibrating your calibrants. So anyway, I think we're probably, we're 2 minutes before lunch. I will be here during lunch if you have questions. If you want to look at that other data set, there was a pre-desalt and a post-desalt data set I had you download. We looked at one of them. The other one will have the same exact numbers, so you can open it up and practice it from scratch if you want. And if you have questions, you know where to find us.